Okay, thanks so much, Andrea and Bede, for putting together this kind of fun mini symposium. So I'm going to talk about kind of there are two different parts to my talk. The first will be using machine learning to classify and predict structure property relationships from AFM images. And the second will be a recent project that we did on artifact detection in PF-QNM. And so this is work that I've done with Ishita Chakraborty, my partner in crime on all of this, and she's down at Cognite in Houston. So the first part really focuses on how can we use machine learning to improve our interpretation of the AFM images. And we tackled two different scenarios. One was a classification problem where we wanted to ask a question about a particular kind of material. They're called impact copolymers. They're ubiquitous in the chemicals industry, a very common kind of polymer blend where you have a polypropylene matrix, like a stiff material here in the background, and then these rubber domains. And chemists can formulate these ICPs in so many different varieties where they're varying the distribution, the morphology, the density of these rubbers to achieve particular ultimate bulk mechanical properties. And so the first question that we had was, could the ICP material excuse me, be identified just based solely on its AFM image? So if you feed an AFM image into the machine learning tool, can it tell you which ICP it was? And then the second part of this project was a more challenging question which was, can we use the AFM images to predict a bulk mechanical property, such as the Young's modulus or impact toughness, which really kind of goes to the holy grail of these structure property relationships that we're after as microscopists. We study these structures on the nano or micro scale, and a lot of times there is trying to correlate or formulate some bulk property, and there's always an intuition, but the question was, could we actually come up with some kind of quantitative correlation now between these different ICPs, because they are formulated to have different mechanical properties. And so what are the different parameters that our machine learning models would be looking at or exploring for any of these tools? So the size of these rubber domains, and if you actually look carefully, not only are there rubber domains, but then these rubber domains are ethylene propylene domains, and then within them are ethylene inclusions. So you've got these domains and inclusions in terms of their sizes, their density, the distribution. And so that you can just get from kind of a phase image, right? Where the phase image is giving you really good contrast between the inclusions, the rubber, and the surrounding matrix. And then later we added another dimension of a quantitative mechanical measurement, so that we added in PF-QNM, where we can now quantitatively measure the deformation, the modulus, and the dissipation. Just a note, all our quantitative measurements for this study were focused on the rubber domains. While one could do quantitative mechanical measurements on the polypropylene matrix, and there is some thought that the mechanical properties of the polypropylene matrix does change between these. When you do PF-QNM, we had to pick one material or the other to get the quantitative data on, because there's a very large range of spread in modulus between the rubber and the polypropylene matrix. So at least for now, we were focusing on the quantitative measurements on the rubbers. Okay, so the first step in kind of all machine learning experiments and measurements are the data collection and pre-processing. And Bede already alluded to this throughput being a real challenge for AFM, especially for machine learning, because you need a lot of data so that you can train the models well. And so we had two different kinds of data. We had AFM phase images that we collected on these ICPs. And even with phase imaging, which you can do faster than the peak force, having consistent net repulsive data was really important. All these samples have to be cryotomes, so areas that had significant cutting marks had to be avoided. And thus, we ended up actually having about 5 samples, and we collected 80. So good data, we were able to get 80 images on each sample. We probably had to throw out about half the data that we collected. And we limited to 10 micron by 10 micron scan sizes so that we can move, so that we can collect more quickly. The peak force QNM is a slower measurement. And so we had to resort to automation, which Bede had described earlier, in order to get reasonable sample sets. And here we had expanded to 9 impact copolymers. And we wanted to, so ultimately we got 45 images per sample using the automated setup with AutoMet that Bede had described earlier. We collected smaller image sizes, 4 microns by 4 microns, to try and speed up the acquisition. And then, as Bede had alluded to, we also did check the tip quality every 15 images, which of course just adds to the throughput. But with the automation, it became very reasonable to do that. We did resort to some data augmentation tricks to at least increase each sample set by a factor of 5. And like I mentioned, we screened our AFM images for clean and consistent artifact-free images. And this, again, is super important. I can't overemphasize this enough, that it's all about having a consistent, clean data set in order to train the model effectively. And so this is just an image for the peak force data that we collected. The phase data was actually collected on a multimode. The peak force we collected on an icon, and you can see that we've got our, here we had 3 ICPs set up at a time. Here was our tip check sample, and just automated, and it would run all day, set up in the morning, and it would just circulate through all the different samples and the tip check and collect our data. And then the different AFM data needed different pre-processing. So for our phase scale, we simply normalized the data so that the absolute phase degree information was discarded and only the relative phase between the 2 components was captured. Peak force, there's a lot of different channels that are collected. There was banding in the adhesion and indentation, so we decided to focus instead on the DMT modulus, deformation and dissipation. The DMT modulus we had to clean up and go through some filtering, and then the deformation and dissipation were actually very clean data and we could just use as is. And so we use a convolutional neural network to do this classification and structure property correlation measurements. Again, our sample set was relatively small, that we were able to increase a little bit by data augmentation. We used a ResNet for the classification and correlation, where we randomly selected 80% of the data to train and then validate with the remaining 20%. And so for the peak force data, again, the numerical information was retained in the model input, whereas for the phase images, the images were just scaled by between 0 and 1. All right, and this is just a reference for the ResNet.